Hey, this is Mr. Mitchell with a video on motion. Now, motion is defined if an object's position changes against a background that stays the same. There doesn't appear to be anything in the backdrop of this lady who is dancing here, but you can tell from the way um, the frames have it that she is moving. I presume that she is moving in this direction, but nothing in the background is moving either. But while she is here, we have this guy and person on the bicycle. They are moving this way. Things in the background, you know, would be staying the same. And same thing with this guy here. Now, yes, I know we have the Earth that is a moving object. It is rotating on a daily basis. It is revolving around our sun, and it takes all year. So technically, all these things in the backdrop are moving, but our definition of motion doesn't really take into account for that. The things like the runner and the bicyclist and the dancer are in motion because there is a stationary background behind them, and that stationary background is called a frame of reference or a reference frame. And you can see we have kind of a similar thing here. We have two pictures of this automobile, one picture where it's to the right of the tree, one picture where it's to the left of the tree. So you can presume that the car is moving. All these things in the background do not appear to be moving, but this appears to be moving, and that's what we define as motion. Speed. Speed describes how fast an object moves. It's a definition you've known for a long time. But to find speed, you must have two quantities. You must have distance traveled and, well, the time it took you to get to that distance. Now, whenever you were in the back of your car and you hollered up at Daddy and Mama, how long is it till we get there? And they say, oh, we're about there. You might look at the speedometer and look at it and say 55 and say, go faster, Daddy, or go faster, Mama. But that 55 is not going to be a constant speed. 55 miles an hour or 65 or whatever you look at the speedometer is just the speed at that moment. And it's almost impossible for a vehicle or even a person to truly go at constant speed. That car that your mom or dad is driving, it had to crank up at some point and accelerate to get to 55. And chances are at 55 miles an hour, it is not staying exactly at 55 miles an hour, probably going accelerating a little, probably decelerating a little, depending on the traffic, just depending on it is a human driving. So what we take is an average speed. The average speed, literally the distance traveled over the time it takes to get there. And that's what we're calculating whenever we're calculating this distance over time. Now, we have what's called down here a distance over time graph. And yeah, I'd like for you to know some things about this distance over time graph. This time here, of course, is going to be in seconds, and that's what the unit is in the time, in the speed, distance over time formula. It's going to be in seconds, and the distance is going to be in meters. And I guess you could put anything right here. I will presume this is like a walker. So the SI unit for speed is meters per second. That's meters per second. So whenever you're calculating the speed, you're wanting to calculate meters per second. Now I know you have heard miles per hour all this time of your life, but we're going to scientifically calculate it as meters per second. So back to this distance time graph, this person apparently is going fast, and whenever you have a graph, it is angled up pretty high if you have fast, because after 1 second they have walked a long way. They have walked, I guess, 1 meter here. Somebody who is going slow in that same second will have only gotten this far. So that is way less than 1 meter. So on a meter distance time graph, Those walking fast will have a higher angle, I suppose you would say, as to those who are walking slow. Now, we know that everything doesn't go in constant speed. In fact, very few things do. This right here, by making a very straight line, a very unwavy line, it means that it's representing constant speed. But how are you going to walk at that constant speed? Generally, you have acceleration, which you can see is when the line curves up, you have some acceleration or speeding up going on. And when the line curves down, you have some deceleration, the curving down of the line, some slowing down that's going on. Now, in reality, if you were walking, you would probably have a little bit of acceleration and you'd probably have a little bit of deceleration, and it would probably be a line that looks like the fast or the slow line, but just with some curvy increments to it. Now, if you were to ever stop your walking, you would have a straight line across. That's not meant to be curved up. I accidentally curved it up. But if you stop, time still goes on. I mean, the seconds are still ticking off, but you would have a straight line across is what you would have. So that's a little bit about the distance over time graph there. Now there is a term called velocity. We use the term velocity almost the exact same way as we use the term speed. It's synonymous, I guess you might say. However, there is a slight difference in velocity and speed. Velocity usually has a direction to it. For example, if you had a football player that ran from the 20-yard line to the 30-yard line, you could calculate the distance, well, you got the distance right here, over the time it took him or her to run that. I guess it would probably be a him to run that distance, and you could calculate the velocity. But we know if you watch any kind of football that chances are good this person ended up taking the ball and then they went out this way and then they found the hole, cut through the line, and then they end up going this way, and they may have even turned back around to try to get some more yardage, and eventually they got, and in this case it looks like from the 30 to the 20, they got 20 yards. But that would be when you calculate speed. If you calculated speed distance over time, the distance is going to be 20 yards, regardless of how much time it took and how many curves and waves it had. But if you're calculating velocity, you can have a speed going in this first direction, a velocity going in the first direction, a velocity going in the next direction, and so on and so on. And you can have all kinds of velocities. And it is indicated often on a map, not on a map, but indicated by like velocity is 3 meters per second north or 2 meters per second east, or sometimes velocity is noted by a plus or a minus. See, the speed up here, you're going 2 in one direction and 2 another direction because the quantity of speed does not have a direction to it. If it goes, it's going a distance, and you calculate it over time. But if you have velocity, you do have that direction to it. Now, you notice here we have distance over time equals velocity. You calculate velocity the same way you calculate speed, distance over time. It's just velocity may have further distinction with it. Now, think about this. I don't know if you can tell, but this is a little bitty pink van that is going in this very crooked road. If you have a constant speed, you could not have this. It would have to do some kind of slowing down. But if you're calculating the speed, you're taking the total distance. So from here, this vehicle is going this way. So even if it had a constant speed through here, it would be slower as if it were going straight across there. You see what I mean? So it may be going 55 miles an hour all the way through here, but in an hour it would not be 55 total miles because of the curves in the road. So one thing I would like for you to be able to do is to calculate speed with the speed formula. And you see I have it here, speed equals distance over time. Now, most cases is just something as simple as, well, writing the distance over the time and seeing if you have, oh, what can I say, the correct unit, I believe is the word I'm looking for. So let's see what we have here. We have a sailboat that travels 100 meters in 120 seconds. What is its speed? Keep in mind, speed equals distance over time. The distance is going to be 100 meters. The time, of course, is going to be 120 seconds. Meters over seconds is exactly what you're looking for, but this can reduce down, and when I punched it in the calculator earlier, I found that it was 0.833, and that would be meters per second. Now, what would have happened if this had been 100 meters in 2 minutes? You could have had the 2 minutes, because that's exactly what 120 seconds is. However, you would have had to convert the 2 minutes to 120 seconds before you could get your final answer right here. And that's going to be true right down here. Here we have a plane travels how fast on a 550-mile, 5-hour trip. So let's start out with speed equals distance over time. The distance is going to be, what, 5 hours? No, 555 miles is the distance. And the time is going to be 5 hours. But we are not going to just punch that in the calculator like we did this one, because this one we already had meters per second, but here we do not. We need to convert miles per hour to meters per second. So before we punch anything in a calculator, let's do our conversion. You may remember on our conversion we have to get miles out of here. So to do that, we put it diagonal. We put it diagonal. So 1 mile equals, and I have the conversion down here, by the way, 1 mile equals 1,609 meters. How did I find that? I just went to Google and typed in how many meters are in 1 mile. So that cancels out the miles, and we have meters up here, but we have meters and we have hours, so we've got to get rid of the hours. So we have to make sure to put the hours diagonal to it. So how many hours will get to seconds? And you may remember that there are 3,600 seconds in 1 hour. Now trust me, if you did not know that, you could have made 1 hour equals 60 minutes, and then on the next line cancel out the minutes to seconds. It would be the same exact total. But we just happen to know, I just happen to know that there are 3,600 seconds in 1 hour. So we cancel out the hours, and lo and behold, all that is left are meters and seconds. So that's when we multiply across the top. Let's see what we have. 555 times 1,609 times 1, which I'm not going to put in. That is 892,995. I'll put it down here just because I'm going to run out of time. 892,995 over, and now I'll have to multiply 5 times 1 times 3,600. Maybe I'll have time on this video to do that. I will try. So we have 5 times 1 I'm not going to put because it's still 5. 5 times 3,600 equals, and that will be 18,000 over 18,000. And that would be meters per second. I'm looking down at my timer here, and I only have about 17 seconds left, but all you would do is punch in the calculator 892,995 divided by 18,800, and that's what you'll get in meters per second. Hey, I hope you've learned a little bit about speed.